Hello, welcome to this video. In this video, let us take a numerical on reciprocating compressor. So let us read the problem. An air compressor taken in air at 1 bar and 20 degrees Celsius. So it will be obviously P1, that is P1 1 into 10 power 5 Newton per meter square, and temperature 1 is 20 plus 273, that is equal to 293 Kelvin. And compressors the same according to law PV power 1.2 is equal to constant. So the value of small n, that is polytropic index, is given as 1.2. It is then delivered to a receiver at constant pressure. So delivery pressure is P2 is equal to P3 10 bar. So 10 into 10 power 5 Newton per meter square. And the value of R is given for air 0.287 into 10 power 3. I am converting it into joule. So R, you can say 287 joule per kg Kelvin. Now we are supposed to determine temperature at the end of compression. So here in this problem nothing is mentioned about clearance volume. So that means I can draw this diagram such a way that there is no clearance volume. So compressor PV diagram without a clearance volume would look like this. Now we are interested in finding out temperature at the end of compression, so that must be T2, and net work done per kg. So work net we should find out, and we should also find out work done and heat transfer during compression. So that means W1 to 2 separately during compression and Q1 to 2 separately. So that is what is during compression, right? So T2, let us go for finding out the first sub question, that is T2. Now how do we find out T2? We know that during process 1 to 2, P1 V1 power n is equal to P2 V2 power n. Okay. So process 1 to 2, we know that P1 V1 power n is equal to P2 V2 power n. Actually volume is irrelevant here, so I would like to eliminate volume here. So PV is equal to MRT equation I will use. I want to eliminate volume, so in place of volume I can write MRT by P, and we know that I am going to replace this V here, alright, but MR will get cancelled out, so I will not write MR. So in place of V I will write T by P. So P1, in place of V1 it will be T1 by P1 whole power n is there, must be equal to P2, in place of V2 I will write T by P. So T2 by n divided by P2 by n, P2 power n. Now that can be T1 power n divided by, this will go to the numerator. We can write P1 power n minus 1, because this when this P1 goes to the denominator it will be minus 1, and if you add the power that will be n minus 1. Similarly T2 power n divided by P2 power n minus 1. So we can write now P2 by P1 whole power n minus 1 is equal to T2 by T1 whole power n. Or we can write T2 by T1 must be equal to this pressure ratio Rp power n minus 1 by En. So that is what we wanted to do. So now we can write T2, alright, because we know this pressure ratio. We can find out pressure ratio separately, that is what? Rp is equal to, now Rp we already know from here, Rp is equal to P2 by P1. Now P2 is 10 bar and this is 1, so even if you multiply it by 10 power 5 it will be cancelled out, so Rp is 10. Okay, so T2 is equal to T1 Rp power n minus 1 by n we can write. Now T1 is known to us 293 and Rp is 10 power Is n value is given as 1.2 minus 1 divided by 1.2. Now let us recalculate it. 293 into 10 power 1.2 minus 1 will be 0.2 divided by 1.2. Okay. So that will be 430.065. So T2 430.06 Kelvin. So that will be our temperature after the compression. Temperature after compression is 430.06 Kelvin. Now let us go to the second question. Let us go to the second part of the question. Now second part is W net. Now I think W net equation we have derived for without clearance volume, we had derived this W net equation, right? Now W net is equal to n by n minus 1 P1 V1 into Rp power n minus 1 by n minus 1. Solve it. 1.2 divided by 1.2 minus 1. Now P1 is 1 into 10 power 5. Now V1 is not known. Now what shall we do? Instead of this P1 V1, it is better we can go for MRT1. MRT1. Okay, I will rewrite this equation. We can always, as long as the working fluid is ideal gas, we can use this. Alright. Rp power n minus 1 by n minus 1. Now in place of this mass I will not calculate because I don't have volume. So I will assume mass as 1. Assume mass as 1 kg. And let us do the work for every kg. Alright. Now M is 1, so this is 287 and temperature 1 is 293. So this is our P1, I mean in place of MRT1, and Rp is 10 power 1.2 minus 1 divided by 1.2 minus 1. Okay. Now this will give us the work in joule per kg, because remember we have written mass as 1 kg. So for every kg of working fluid, this will be the amount of work which is required. Okay. So now let us solve this. (1.2) divided by 1.2 minus 1, that is our first term, into 287 into 293 multiplied by 10 power, now this will be 1.2 minus 1 divided by 1.2 and minus 1. Now 236.02 into 10 power 3. So in joule per kg it will be 236.02, or you can write divide by 1000, we will get it in kilojoule. So 10 power 3 cancels out, we will get 236.02 kilojoule per kg. This is our work net. Okay. Now let us go to the last part, that is we want WO122 and Q122. Okay. Now what is WO122? WO122 is, it is a process, polytropic process. Now we can write P1 V1 minus P2 V2 by n minus 1. Now obviously we do not have PV, so we can write it like MRT1 minus MRT2 by n minus 1. And remember we do not have M also, but anyhow MRT1 minus T2 by n minus 1. So assuming that M is equal to 1 kg, I will only substitute R value, then T1 is 293 minus T2 is 430.06 divided by 1.2 minus 1. So that will give me an answer 287 into 293 minus 430.06. So that is the numerator, divided by 1.2 minus 1, that is 0.2. So minus 196.68 into 10 power 3. Minus 196.68 into 10 power 3 joule per kg. And we know why it is negative. Okay. So we can also talk, this is not negative because we have modified the equation such that we do not want to handle negative every time, alright. So work net is also going to be negative in fact, but we have modified this equation so that we do not get negative every time. Actually the equation was 1 minus Rp power n minus 1 by n. Anyhow, for work negative because it is a compression process. For a compression process, sign convention is which we already know, negative because compression, work absorbing process. Okay. This can be also written in kilojoule divided by 1000. So 10 power 3 cancels. So W122. So that is our work net, work 1 to 2. Okay. Now let us go to the last part that he wants us to calculate Q. Now for a polytropic process, Q is given by, Q is given by W into gamma minus n divided by gamma minus 1. So this comes from our basic thermodynamics knowledge. For a polytropic process, the heat transfer is calculated using this expression. Alright. So we have every expression, that is minus 196. So I will not convert this into joule because none of the other values have units. Whatever unit we substitute in W, the same unit will be Q. So 1.4 minus 1.2 divided by 1.4, that is gamma value for air. Gamma for air is known to us, 1.4 minus 1 here. So that will be minus 196.68 into 1.4 minus 1.2 divided by 1.4 minus 1. So that is minus 98.34. Minus 98.34 kilojoule per kg. Now this is Q122, remember, this is our Q122. Now if you are going for Q122, we are going to substitute W122, that is what we have done. Okay. So this is our answer for heat transfer during process 1 to 2. So let us take few more problems in the next class. Thank you.